This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2018 AP Calculus exam, free response question BC5. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on or highlight the solutions presented in these guidelines, not how the points were awarded. Now, this question was not calculator active. However, I'll show you how to use technology to explore and answer parts of this question, and to confirm solutions where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. This question involves two polar curves, whose graphs are given in the figure. We are also told that the graphs intersect when theta equals pi over 3 and theta equals 5 pi over 3. In Part A, we need to write an expression involving an integral that yields the area of the shaded region R. In Part B, we need to find the slope of the line tangent to the graph of one of the polar curves at theta equal pi over 2. And in Part C, we now have a particle moving along a portion of the curve described by r equal 3 plus 2 cosine theta. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. We need to find the rate at which the angle theta changes at the instant when the position of the particle corresponds to theta equal pi over 3. Part A was worth 3 points. The first point was for writing the constant 1/2 and the limits or the bounds on the definite integral, a lower limit of pi over 3 and an upper limit of 5 pi over 3. And the constant and the limits must be in the context of a definite integral. The remaining 2 points were for the integrand expression. Note that there were other valid expressions if the student used the symmetry in the graphs or evaluated part of the integral involving the constant 16. Part B was worth 3 points. The first point was for writing a correct expression for either dy d theta or dx d theta. The second point was for writing a correct expression for dy dx. And the third point was for the final answer, here 2/3. Note that there was an alternate solution to Part B given on the scoring standard. And this involved the use of the explicit expression for r. But this solution was scored in a similar manner. Part C was worth 3 points. The first point was for writing an expression for dr dt. The second point was for solving for or isolating d theta dt. And the third point was for the final numerical answer with the correct units. Now, let's see how we can use technology to solve parts of this free response question. Part A asks for the expression for area only. But I think we can use technology to find the actual area of the region R. First, here's the integral expression that represents the area of the region R. Using a TI-Nspire, I graphed both polar equations. The graph of r equal 4 is a circle, centered at the origin, with radius 4. The graph of r equal 3 plus 2 cosine theta is a limacon. To find the exact area of the region R, I defined the function little r, and then I evaluated the definite integral. That's the exact area of the region R in Part A. and that's pretty amazing. And on this last line, I just wanted to see a numerical approximation for the area. Here's an example related to Part A of the free response question. I think there are some other interesting regions associated with these two graphs. So find the area of the region R1 and the area of region R2. Carefully set up each definite integral, and then use technology to evaluate and find the areas. In Part B, we need the slope of the tangent line to the graph of r equal 3 plus 2 cosine theta at theta equal pi over 2. To find the slope, consider theta as a parameter and write the parametric equations that describe the curve. They are x equal r cosine theta and y equal r sine theta. Now here I defined x and y using the expression for r. And I used the parameter t rather than theta on the TI-Nspire. The slope is dy dt divided by dx dt, evaluated at t equal pi over 2. That's a pretty quick, accurate method using technology to get the final answer here of 2/3. Here's another example for you to try. Suppose we consider the same polar curve described by r equal 3 plus 2 cosine theta. Find the slope of the tangent line to the curve when theta equals pi over 4. In Part B, find the points on the curve where the tangent line is horizontal or vertical. And to visualize Part A, I sketched the graph of the polar equation on the TI-Nspire, and I added a graph of the tangent line. In Part C, I don't think there's much I can add to this solution using technology, but there are some nice conceptual ideas here. First, we need to use the chain rule to write dr dt in terms of dr d theta and d theta dt. And then we need to find dr d theta and substitute into the initial equation. We need to find the rate at which the angle theta changes with respect to time. So that means we need to solve for d theta dt. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. So that means that dr dt is equal to 3. And we want d theta dt at the instant theta equals pi over 3. The final answer here is minus the square root of 3. Since Part C involved related rates, here's a final example involving some other related rates problems. Part A involves the distance between two ships, and Part B involves a particle moving along a curve and the distance from the origin. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions and of how to use technology to solve some of the parts of this problem, to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.